Okay, so today we'll start talking about matrices. So recall we've already encountered matrices in our study of linear transformations when we are looking at maps from R2 to R2, which are what we call linear transformations. And in this context, matrices appeared as encodings of linear transformation. So a linear transformation was essentially determined by 4 numbers A, B, C, and D, and arranging them in a 2 cross 2 matrix form somehow was the correct way of encoding this linear transformation. And we saw that the operation of composition of linear transformations was precisely captured by the operation of multiplication of matrices. Okay? So that is already a context in which we have encountered matrices. Now here's another context in which you probably have already seen matrices. So this is likely to be a somewhat more familiar context, which is in trying to solve systems of linear equations. Okay, so here's an example. Let's consider the system of 2 equations, 2x plus 3y equals 1, 3x plus 4y equals 2, and there are 2 unknowns x and y. So the question is to solve. So solve for x and y, and so of course there's always a way of trying to eliminate one variable in favor of the other and so on, but here's the sort of the easy way of doing it, a somewhat clean approach, which is to rewrite this equation in matrix form. So we rewrite the system of equations in the following way. We consider the 4 coefficients 2, 3, 3 and 4, form the matrix, and this equation can just be written as this matrix multiplied by the column vector or the 2 cross 1 matrix x comma y. So the product of these two gives the coefficients 1 and 2. Okay. So this system is exactly equivalent to this equation written in matrix form. Okay. And as is easy to check, the definition of matrix multiplication says you need to do 2 times x plus 3 times y. That's the first coordinate that you get when you multiply them out, and the second one is 3 times x plus 4 times y. Okay. So and when you equate these two, all you get is the equations 2x plus 3y is 1, 3x plus 4y is 2. Okay. So these are 2 equivalent ways of writing the same thing, but this suggests a way of solving it. So what's the usual way of solving such systems of linear equations? We multiply both sides of this equation by the inverse of this matrix. Okay. So what does the inverse mean? So here's the thing: if you have the matrix of coefficients 2, 3, 3, 4, so what does the inverse matrix mean? Well, it's the matrix which when multiplied with the matrix M will give you the identity matrix. Okay. So let M inverse be its inverse. In other words, it's the matrix which has the property that this into this is what we call the 2 cross 2 identity matrix, and it's immaterial which order you multiply them, whether you do M into M inverse or M inverse into M, gives you the identity matrix. Okay. So let M inverse denote the inverse of this matrix, and so there is a, for a 2 cross 2 matrix there is a nice formula which tells you what the inverse is. So what's the general formula for a 2 cross 2 matrix? Well, here's what you do. So given for, let's say, so here's an aside, if I have a 2 cross 2 matrix A, 4 coefficients A, B, C, D, the inverse of this matrix has the following easy description. You do the reciprocal of the determinant of the matrix, so it's 1 by the determinant, remember, was AD minus BC times the entries here are just DA minus B minus C. So this is just a prescription which works for 2 cross 2 matrices. Trying to do this for 3 cross 3 and so on is somewhat harder, of course. So it's this answer, and notice of course that and the inverse only exists provided the determinant is not 0. Okay. So you can't invert matrices for whom the determinant is 0. So let A be a 2 cross 2 matrix with determinant non-zero. So, determinant of A, which is AD minus BC, should be non-zero. Okay, only then can you find the inverse. In this case, we are okay because the determinant of M is 4 into 2, 8 minus 9. So, the determinant here is a minus 1. The determinant of M here is a minus 1. And applying this formula here, it says that the inverse of M can be computed as follows. The inverse of M is just 1 by minus 1 times dA, and then you do minus 3 minus 3. So, that is the inverse of this matrix M. And now what we do is just multiply. So, now we are almost through. So, to solve the original system of equations, so recall the original system was re-expressed as follows. It is the matrix M times the vector xy is the matrix 1 2. So, now we multiply both sides of this equation on the left by M inverse. So, this became M inverse times M times xy is M inverse times 1 2. Now, M inverse times M is the identity matrix, and the identity matrix, let's call it I, multiplying xy will just give you back xy. Okay, so, that is the whole point of doing this. The left hand side is now just become x and y, whereas the right hand side now is easy to compute. So, M inverse we just computed is, so there is a 1 by minus 1 which I will take inside, it is minus 2 3 3 times 1 2. So, it is just a question of multiplying these two things out. So, that is easy enough. It is minus 4 plus 6 is 2, it is 3 minus 4 is minus 1. So, we conclude that finally x must be 2 and y must be minus 1. Okay. And it is easy enough to check that these two will do the job. You just have to plug it back into the system of equations and see that they satisfy. Okay. So, this is the standard place where you would have seen matrices before when you want to solve a system of say n linear equations in n unknowns. Now, let us do another example which is sort of interesting because we have already seen it in an earlier context. So, let me do another example of solving linear equations. Example, find a polynomial in one variable, so it's polynomial f of x of degree at most 2 satisfying the three conditions f of x1 is y1, f of x2 is y2 and f of x3 is y3. Okay, where x1, x2, x3 are three distinct real numbers, x1, x2, x3 are three distinct real numbers. And the y's are just any arbitrary real numbers, not necessarily distinct. So, these are just reals. Okay. And of course, recall this is exactly the problem of interpolation, right. So, here I have just taken a special case of interpolation where you are looking for a polynomial of degree at most 2, and so recall this is just the question of polynomial interpolation that we studied right at the beginning. Interpolation. So, you might wonder why this is sort of making a reappearance now in the context of solving systems of linear equations, right. So, isn't this about finding a polynomial which satisfies a set of constraints? Okay. Now, it turns out that this is in fact nothing but a system of linear equations. Okay. So, let us see how this can be recast into this form. So, what we are looking for is a polynomial of degree at most 2. So, what we want is f of x. So, let me just write it as follows. Let me call it a plus bx plus cx squared, right, because that is how a polynomial of at most degree 2 looks like, where what are a, b, c? Well, a, b, c are some real numbers and those are really our unknowns. So, these are the three numbers that we want to find now. So, these are our unknowns. Okay. So, the coefficients of this polynomial A, B and C turn out to be the three unknowns that we are looking to solve for. And what are we given? We are given three conditions, right? So what is given? So we want to find ABC given the three conditions that f of x1 is y1, f of x2 is y2 and f of x3 is y3. So we'll write those three conditions down. So when you substitute x1, this polynomial becomes a plus bx1 plus cx1 squared. That's given to be some number y1. So x's and y's are constants here. Similarly, a plus bx2 plus cx2 squared is given to be y2, and a plus bx3 so this is nothing but a system of three linear equations in the unknowns a, b, c, with coefficients being 1 x1 x1 squared, 1 x2 x2 squared, and so on. Okay, so let me rewrite this in matrix form. So let's form the coefficient matrix. So this is just the following. Consider the matrix M, 1 x1. So it's 3 cross 3 matrix now. X1 squared, 1 x2 x2 squared, 1 x3 x3 squared. That's the matrix M. And what does the system now become? The system becomes the following. It's the matrix M. So this is the same thing as equivalent to M times the vector A, B, C. That's the unknowns, becomes y1, y2, y3. Okay, so we've rewritten our system of equations. And now all we required to do is try doing the same thing as before, which is to sort of multiply both sides by the inverse of M. So what we want is now, therefore, well, this equation therefore can be solved as follows. So let's do it here. The solution A, B, C is therefore just the matrix M inverse multiplied by y1, y2, y3. Okay, so let's keep this in mind. That's the solution that we finally want for the three coefficients A, B, and C. Okay, so what does that really mean? We need to compute the inverse of this matrix M in order to figure out how this is to be solved. Now, finding the inverse of a 3 cross 3 matrix is somewhat trickier than finding the inverse of just a 2 cross 2 matrix. So for a start, what we will need as before is the determinant of this matrix M. Okay. Now, this particular matrix M, which has this very particular form, 1 x1 x1 squared and so on. So such a thing is, it has a name. It's a very special matrix. It's called the Vandermonde matrix. Of size 3, if you wish, of size 3 cross 3. So there's a Vandermonde of any size, n cross n. So here's the 3 cross 3 Vandermonde matrix, that's M, and the corresponding determinant, the Vandermonde determinant, has a rather well-known explicit expression. It's rather surprising at first if you haven't seen it before. So let me tell you what the answer is here. Okay, so here's the fact. The determinant of the 3 cross 3 Vandermonde matrix has an exceptionally nice form. It's just the following product. Just a product of three terms, x3 minus x2, x3 minus x1, and x2 minus x1. Okay, so here's the first exercise. Try this out. Compute the determinant of this matrix using whatever properties you know of how determinants are computed. So exercise prove this. Calculate and prove that this is in fact the case. Okay, so the determinant is this nice product. And now what we need to do next is compute the inverse of this matrix. So the prescription for the inverse is the following. So how do we compute M inverse? So M inverse is, as before, it's 1 by the determinant times another matrix here. Okay. Now this matrix over here, sometimes called the cofactor matrix. So let me maybe just call it or the adjoint. So let's give it the name. Let's call it C for now. Okay, it's 1 by determinant times a matrix C, where what is this matrix C? C has the following description. You want to figure out what is the ijth entry of C. Okay, C is again a matrix n cross n, in this case 3 cross 3, and you want to find the ith row jth column entry of C. It's obtained as follows. So here's the procedure. So let me describe the procedure. You take the matrix M. So here's the matrix M itself, and you do the following. You look at the ith column of M. Okay, so I take the ith column of M, and I take the jth row of M. Okay, so you take the ith column and the jth row of M, and you delete. You remove these two things from M. Okay, you remove both of these from M. What you're left with now is a matrix of size 1 lower. So in general, if it's an n cross n matrix, you'll be left with something of size n minus 1 cross n minus 1. In this case, since M is 3 cross 3, you would get a 2 cross 2 matrix, and you take the determinant of that 2 cross 2 matrix. Okay, so here's a deleted matrix whose determinant you take, and Cij is that determinant multiplied by a certain sign. Okay, so it's this determinant times plus 1 or a minus 1, and the sign is given by this explicit formula. It's minus 1 to the I plus j. Okay, so such an expression is sometimes called the minor of the corresponding element, whatever jith element of M and so on. So in any case, if you've not seen this before, it's not a big deal. I'm not going to worry too much about this. So suffice it, I mean, for our purposes, it suffices to know that there is an explicit expression for the inverse of any n cross n matrix given in terms of determinants like this, 1 lower size determinants. Now M inverse is therefore has this very explicit description. So in our case, we can just use, since we know M, we just delete the appropriate row and column, compute the determinant, multiply by a sign, things like that. Okay, so the inverse can be computed. So let me just tell you what the inverse of M looks like. So I won't write all 9 entries, maybe just the entries in the first column. So the claim is the inverse of M is 1 by determinant of M times, okay, so times the matrix C that I wrote out, and here are the entries of the first column of C. Okay, so it is x2 x3 times x3 minus x2. This is x2 squared minus x3 squared. This is x3 minus x2. And then of course there are another 6 entries here, second column, third column, which I'm not writing out at this point. Okay, so exercise number 2, check that these entries are correct. So exercise, check these using the description that I just gave you. So exercise check. Okay, so those are the entries of C, at least the first column entries of C. Now one can of course simplify this, because the determinant of M again has this nice form. It's just a product of 3 terms. This is x3 minus x2, x3 minus x1, x2 minus x1. Okay, so this product is sitting on the denominator. Okay, so you can sort of cancel some terms out from the first column. Now that's again something that you should do, but I want to just complete this calculation here. Recall what we wanted to find in the first place was the polynomial f, right? So the polynomial f was actually a plus bx plus cx squared. So it's of course composed of, I mean, the 3 real unknowns are a, b and c, but suppose I wanted my polynomial f of x, the full polynomial, not just the 3 coefficients separately. So then how do we go about finding f? Okay, so assume for the moment that I have figured out what a, b, c are from my description of M inverse and so on and so forth. By using that this property here, it will tell me what a, b and c are. But let me recover f from a, b, c. So how do I figure out what f of x is? Given a, b, c, how do I find f? observe this is just the following. Again, it has a description in terms of matrices. So here's what I can do. I know the column vector ABC, that's the thing that I am determining from this procedure. But if I want to put them back, stitch them back together to get the function f, all I do is multiply that column vector by the row vector which has the entries 1, x and x squared. Okay. Why? Well, all you have to do is just multiply them out. 1 times a plus x times b plus x squared times c. That's exactly how you do the multiplication of these two things. Now observe the following fact, that here's already something slightly different from what we have seen so far. The entries of this matrix or this vector are not numbers anymore. So observe, there are x's now appearing. So these are not, no, they're not real numbers, for instance. Okay. Instead, they are actually elements, well, they're variables here. But that's perfectly okay. So whenever you encounter matrices, it's not necessary that the only matrices that it's okay to have matrices which don't have real numbers or constants in them. It's okay to have, say, other kinds of objects. It's fine if you have matrices which have polynomials in them, for instance. Okay? Or more generally, it's okay to have matrix entries be anything which you can perform addition on or multiplication on and so on. Okay? So the kinds of things that you put into matrices or into vectors, those entries really only need to have some sensible notion of addition and multiplication defined. Okay? So matrix entry, so this is another point to note here. Matrix entries need to have a notion of addition and multiplication between them. Okay? That's pretty much all you need. You don't need anything else. So it's okay to have 1x x squared be matrix entries, because we do know how to multiply, so there are polynomials in x and we know how to multiply two polynomials together, for instance, or we know how to multiply or add polynomials, etc. Because this is all that will really come up when you try and multiply or add matrices. Okay, so let's get back to this. We know that the polynomial is just 1x x squared times the vector ABC. So we could go ahead and say this is just the vector 1x x squared times, well, the matrix M inverse. So remember, ABC is just M inverse times y1, y2, y3. Okay, so we have the polynomial f of x can be obtained in the following fashion. You take the matrix M inverse and you sort of sandwich it between a row vector and a column vector, the row vector being the entries 1x x squared, the column vector having entries y1, y2, y3. Okay? So this is the sort of the final expression. Here's the polynomial f of x that one wanted. Okay? But let's just do, since we wrote out the first column of M inverse, let's just do one step of this. So we take f of x, as I said, is just 1x x squared times M inverse times, well, this column vector. Let's do the following. Let's first multiply these two things out, this row vector 1x x squared with the column vector M inverse, with the n cross n matrix, 3 cross 3 matrix M inverse. So this calculation is the following. It's 1x x squared times, well, I just wrote out the entries of M inverse. So after simplifying, after dividing by determinant and so on, so you sort of get 3 entries here. Okay? Now when you multiply these two things out, here's what you will find. So there are 3 entries. So let me just tell you what the first entry looks like. It's just x minus x2 times x minus x3 divided by x1 minus x2, x1 minus x3. And similarly, the other 2 entries are going to be, so let's write them out as well, x minus x1, x minus x3, x2 minus x1, x2 minus x3. So I sort of wrote them out. So this should have been a row vector rather than a column vector. Okay. So these three things should have been written really across a row. Let's just do that. So its first entry is this. The second entry of this is x minus x1, x3, and the third entry would similarly be the corresponding. So let me just skip the third entry. Anyway, this is something for you to check. So check again. So exercise, check that this is correct. Check this equality. Okay, and you should already figure out that these are things that we have seen before, right? Each of these three things has appeared when we talked about Lagrange interpolation. In fact, these were exactly those 0, 1 polynomials. This polynomial that's in the first entry here is precisely the polynomial which takes the value 0 on x2 and x3 and takes the value 1 at x1. Similarly, entries 2 and 3 will be the ones which take 1 at x2 or x3 and 0 on the other two variables. Okay, so finally, what's the final answer? The function f of x that we were looking for is just this row vector multiplied by the column vector y1, y2, y3. Okay, and if you complete the calculation, you'll see that's exactly the formula for Lagrange interpolation. Okay, so the final step. So I'll again leave this as an exercise. So finally, check that the formula that you get for f of x using this approach in terms of linear transformations, in terms of solving systems of linear equations, is exactly whatever you would have gotten by doing Lagrange interpolation. x2, x1 minus x3 plus two more terms, y2 into something plus y3 into something. Okay, so what this serves to demonstrate is that the same problem can often be approached in more than one way. What we did earlier with Lagrange interpolation is sort of start with the idea of this whole 0, 1 idea of trying to find polynomials which did the 0 or 1 thing and using that to quickly get the answer, right? So that allowed us to pretty much instantly write out the candidate polynomial. Here it's a somewhat more systematic procedure. We don't really start with that brilliant idea, but just a systematic way of solving for the three coefficients that occur in the polynomial and thinking of the three conditions as just being three linear equations for those variables. Okay, so this is somewhat more systematic procedure, but at the end of the day, it pretty much what pops out is exactly the same 0, 1 idea. Okay, so we'll talk about other applications of matrices next time.